Hi everyone, today I'm going to talk about the discretization of the convective term in the Navier-Stokes equations. Here we are going to focus mainly on the first order and second order upwind schemes. The Navier-Stokes equations in a differential form can be written like this. The convective term is shown here inside this red square. Okay, this is the convection term through the control surface S as shown here. This is a volume control, omega is the volume, and S is the surface of this volume control. The convective flux has to do with the convection through this control surface S here. So let's see. Here we are going to calculate the convective flux through the mutual phase F of the two cells 0 and 1 as shown here. So we are going to calculate the convective flux through this phase F. Here S is the vector surface area of the phase, which is shown with this vector. Okay, and delta X as shown here with x0 and x1 being the position vector of cells 0 and 1 respectively, indicates the vector connecting two cells 0 and 1 here. Okay, in fact the vector delta x is connecting the centroids of these two cells, cell 0 and cell 1. Okay, in other words, delta x is the vector between the cell centroids. The convection term in an integral form can be written like this. Okay, here it shows the convective flux among all the cell faces here. Okay, sigma is the in fact indicates the summation, right? This summation is performed over all the faces. Okay, however, here we are going to be we are going to focus only on the cell face area which is mutual between the two of these cells, cell 0 and cell 1. Okay, for a general quantity phi, the convection term can be discretized as this equation. Here phi is a general scalar quantity, okay, and it can be discretized using this equation. Here phi and m dot, the subscript f, are the value of the scalar quantity phi and the mass rate at the surface f respectively. Okay, the mass rate, in fact, is calculated by multiplying the fluid mass density by the flow velocity and then by the cross-sectional area. The cross-sectional area is S, as is shown here, right? The challenge here in this equation, in fact, is how we are supposed to calculate the value of phi on this phase. Because in finite volume, the value of the variables are stored in the cell centroids. Okay, so this is the point. How are we supposed to calculate the value of phi in this phase? Before presenting the Upwind schemes, it is worthwhile outlining the main difference between the diffusion and the convection terms. The diffusion process affects the distribution of the phi along its gradients in all directions, whereas convection spreads influence only in the flow direction. Therefore, for proper discretization of the convective term, we need to use a method that takes the flow direction into account. In other words, the method must have transportiveness, must be transportive, which indicates that the scheme recognizes the flow direction and consequently the strength of the convection with respect to the diffusion. Okay, this is the key point. In this regard, various methods were put forward to resolve this problem. However, among them, the most popular and the most accurate approaches are the first order and second order Upwind schemes. Okay, let's see now what is the first order Upwind scheme. The first order Upwind scheme can be written as these equations. Okay, as can be seen, the first order Upwind scheme approximates the phase cell, the phase value of phi by its value at the node upstream, as shown here, right? In other words, when the flow is in the direction of positive x-axis, what will happen is that the phase value, the value of phi at the phase f, is exactly the value of phi at the cell 0 value. Okay. On the other hand, when the flow is in the direction of negative x-axis, the phase value f is equal to the cell 1 value. Okay. It is in fact equivalent to using a forward or backward differential scheme. This scheme is in fact highly stable, and you can always get a result using this approach. However, it is highly diffusive. It is because its leading truncation error term is diffusive. In other words, it resembles the diffusion term. To show this, we use the Taylor series expansion about 0. Okay. In this equation, H denotes higher order terms. The first order upwind only uses the first term, right? It only uses this term. As can be observed, its leading truncation error term is diffusive. It resembles the diffusion term. Okay, it is highlighted here. This numerical diffusion gets larger in multidimensional problems if the flow is oblique to the grid. The truncation error then produces diffusion in the direction normal to the flow, as well as in the streamwise direction. This is a particularly serious type of error. Therefore, to solve this problem, the second order upwind method was put forward, which is shown here. Okay, this is the second order, and these expressions show the second order upwind scheme. The idea behind the second order upwind is exactly the same as that the first order upwind. However, the main difference between these schemes is the presence of the second term inside the square brackets in the second order scheme. Okay, these terms here, these terms, this term is there was no such term like this in the first order. The first order, in fact, just contains the cell, the values at the cell centroids. But this scheme has another term also. What are these terms? These are, in fact, the linear interpolation, the linear interpolations of the values of the scalar quantity phi at cell centroids to the mutual phase of these cells. Okay. In these gradients, the subscript r of the gradient of phi signifies the reconstruction gradient. Okay, r here is in fact signifies the reconstruction gradient. This method is more accurate than the first order upwind scheme, but in regions with strong gradients, it can result in phase values that are outside of the range of the cell values. Therefore, it is necessary to apply limiters to the predicted phase values. This can be done by limiting the unlimited reconstruction gradients. So how can we do this? We can limit the unlimited reconstruction gradient, which is shown here by the superscript u. U means unlimited. Okay. Uh, so we will use a factor alpha f as shown here. Okay. This alpha f is in fact a factor which is used to limit the value of the reconstruction gradients. Okay. However, how can we define alpha f? Alpha f is defined in fact based on the minimum and maximum values of the scalar quantity phi found in the neighboring cells. Okay. Now, let's now evaluate the accuracy and performance of both the first order and second order Upwind schemes presented here. Here we will consider a fluid flow whose temperature above the diagonal is 100 degrees of Celsius. Okay. On the other hand, below the diagonal is 0 as shown in this figure. Okay, so above the diagonal the temperature of the fluid is 100 degrees of Celsius. However, uh, below the mm, below the diagonal, this temperature is 0 degrees of Celsius. Ideally, the temperature has to be exactly 100 degrees of Celsius everywhere above the diagonal and exactly 0 degrees of Celsius everywhere below the diagonal. But let's see the performance of each scheme. Here we have evaluated the performance of these schemes using two different measures. Okay, the one on the top of the one on the top of the screen is the more coarse grid. However, the one on the bottom of the screen is the more refined grid. As can be seen, false diffusion can be clearly observed in all the predictions. False diffusion happens due to both the oblique flow direction and non-zero gradient of temperature in the direction normal to the flow. As can be inferred, a proper grid refinement combined with a high-order scheme can minimize largely the false diffusion, which is the case of the prediction provided by the more refined grid combined with the second order upwind, which we can see here in the corner of the screen, the best prediction. Okay. This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.